earlier, we imagined comparing the mean height from a sample of college basketball players to the mean height in the population of NBA players. The mean height for the college players was 78.25 inches compared to the mean of 79 inches for the pros. The p-value for the comparison of these two means was 0.03, so we concluded that the difference was statistically significant. The p-value and the decision to reject the null hypothesis are informative as far as they go, but they do not tell us whether the difference is important because the size of the p-value does not depend solely on the difference between the means. It also depends on the size of the sample and the variance of the population. You can see here that with the same difference between the means of 0.75 inches and identical variance in the population, the p-value is 0.032 for our sample of 100 players. In contrast, it would have been about 0.002 for a sample of 200 and about 0.129 for a sample of 50. Again, the p-value does depend on the size of the difference between the means, but it also depends on sample size and the variance of the population. So we can't use the p-value to help us determine how big or important the difference is. We need another measure to help us decide whether or not an effect has meaning in a practical sense. Effect size is a quantitative measure of the magnitude of the effect. It is not dependent on sample size. There are many different measures of effect size, depending on the type of statistical analysis. In our example with the height of basketball players, we can simply calculate the difference between the means as a measure of the size of the effect. We subtract the sample mean height minus the population mean height and find that the height in the sample is 0.75 inches shorter than the height in the population. Now the recruiter can consider whether 3/4 of an inch is a meaningful difference in the context of height of NBA players. In this case, we have discussed effect size in the same units as the variable of interest. In other cases, however, it may be more useful to discuss the size of the difference in standardized units, which simply means that we convert every measure to a single scale. One common standardized measure of effect size is Cohen's d, which measures the distance between two means in standard deviation units. In our example, the unstandardized measure of effect size, 0.75 inches, may be useful for those familiar with basketball and the height of NBA players. However, measures of other variables like happiness, anxiety, or motivation may not have intuitive measurement scales like length in inches. Or there may be different scales for measuring the same type of variable, such as time in minutes or seconds, or weight in grams or pounds. In these cases, a standardized measure of effect size might be more useful because it would allow comparisons across these different measurement scales. Keep in mind that what is considered a small or large effect may vary from one context to another. Effect size values should always be combined with judgments of practical and clinical importance based on the variable in question. A small effect size for inches of height may not be important, yet a small effect size for tumor growth may be meaningful. Even a large effect size should be viewed within the context of other research in the field and not immediately deemed important due to its size alone.